Hi there, welcome to your second video on trigonometric identities. In this one, we will continue where we left off in the first video, where we will use the identities to solve trigonometric equations. We ended by mentioning that there are many trig identities, but there are only a few that we need to know in our course, and they are these ones. Number 1 and 2 is the Pythagorean identity, which comes straight from the unit circle and the right triangle there. Using Pythagorean theorem, we get this identity. The second one is that tangent of theta is equal to sine over cosine of theta, and that comes from the fact that we have opposite over adjacent, and that's our tangent value. And then we added these 4 extra identities called the double angle identities, because you can see here the cosine angle is doubled and the sine angle is doubled. And for cosine of 2 theta, we have 3 identities. And for sine of 2 theta, we have 1 identity. So basically, we're going to have all kinds of equations where it's your job to figure out which of these 4 is the best one to substitute in order to solve a trig equation. So let's get started. Let's try it out. And here's the problem we left off on. We had 2 cosine 2x. Right away we see a double angle here, so we're thinking maybe we'll use one of these cosine ones. Okay, so let's try. And this equals 1. We're looking for angles between 0 and 360. So to begin, I noticed that this says x and this says 2x. So before even using our identities, I want to approach this one the way we did previously. We've solved ones like this before. Before we even knew the identities, we solved problems like this. And this is how we did it. So let me remind you. I compare this. This says 2x, this is x. That means I'm going to change my domain to match what I see here. So I'm going to rewrite it like this. If I'm doubling that x, then I have to double this number and I have to double this number. So I've doubled 0, which is still 0, and I've doubled 360, which is now 720. So now I can look for angles that meet this equation between 0 and 720. Okay, so I'm solving the equation. I divide by 2 first. Okay, so now I have a simplified trig equation. So I know some angle, never mind that it's 2x here, it's just some angle produces a cosine value of a half. And remember, cosine is the x value. So I have my unit circle here, and I know my goal is to create an x value of a half. And that can happen either up here or down here, right? Because those are both positive x, right? This is an x value of a half, positive. So we can have that angle or that angle. And now I'm just trying to figure out how many angles produce that value between 0 and 720. So the first angle is here. If I spin this, well, if this is a half, then this angle is 30. That means this one's 60. So if I spin 60 degrees, I get my first x value of a half. And then I keep going around and I spin all the way to here. And then I get an x value of a half again. So if this was 60 and this is 60, then this must be 300 to get here. That's 2 angles. But we are now going to 720 because we've made this adjustment for 2x. So you keep going around again. You've come to here, and now you're coming your second time around the circle. So you go once around, and then second time. So it's 360 plus 60 more, 420. And then the last one is you keep going around and you get to here again, and that's 660. So pause and think about those angles on your own just to remind yourself how they work. But there's 4 of them within 720. But those are angles produced by this thing, which is 2x. But now I'm going to take that back to just x. I want to just find out what x is. So divide everything by 2. Divide by 2 here, divide all these by 2. So these are now my answers in terms of x for this question here. All right, let's look at the same problem now using our new double angle identities, because this is the old approach, the way we looked at when we did this adjustment. But now let's look at them in the context of our double angle identities. So one of our double angle identities for cosine tells us that cosine of 2 theta equals this. So I'm going to replace that. I'm going to rewrite that, this cosine of 2x, and replace it by that. That 2 in front still has to be there, see? It's there. So that's the extra 2 here. And then we have that 2 here also. So make sure you see that there's 2 of those. All right, now I'm going to multiply through, and I get 4 cosine squared x minus 2 equals 1. And now I'm going to solve this to simplify it, right? So I'm going to move that 2 over, get a 3. Now I have a 4 here. I'm going to divide by 4. Now I have a square here, so I'm going to take a square root on both sides. When I take a square root here, I have root of 3, and the square root of 4 is 2. Don't forget to put plus and minus when you take a square root. So again, we're looking for angles between 0 and 360. Now it says x here, and we have x here, so we don't have to worry about adjusting our domain at all. We have x here already. So now we're looking for angles between 0 and 360 that lead to a positive and negative root 3 over 2. So here's my unit circle. Again, cosine represents x values. So I'm looking for x values that are root 3 over 2. So here's one time we have an x value of root 3 over 2. And it also happens in the negative side. So here's negative root 3 over 2. Because we have positive and negative here. So here's a positive x value, here's a negative, and we have one angle, another angle, and then we can also have the angles down below. So I'm going to show those as well. We have 4 ways to get that x value of positive or negative root 3 over 2. So what are those angles? All right, if this is root 3 over 2, then that tells us this angle is 60, and this angle is 30. So we know our angles are 30 degrees to get here, 150 degrees to get to here, then 180 plus 30 is 210 to get to here, and then 30 degrees short of 330 to get to here. There's the 4 angles within 360. Notice those answers match exactly to what we got when we did the first approach. All right, so now let's look at this same question again using another one, because we know that cosine has 3 identities. Cosine, the double angle for cosine, has 3 identities. So let's try another one. Here's another one. Cosine of 2 theta equals this. So now I'm going to replace cosine of 2x with all of this, using this other identity, just to make sure it still works. So notice I've made the substitution here. Now I'm going to multiply through, so 2, and this becomes negative 4. Then I'm going to subtract 2 on both sides to get negative 1 here. Then I'm going to divide by negative 4, and I get this. I have a square, I'm going to take the square root, and again I end up with plus or minus, because I'm taking the square root, 1 over 2. Now, I'm looking for sine values. In the last part, we ended up having cosine, but now we're looking for sine. So remember, sine represents y values. So we have our unit circle. I'm looking for y values that are a half. So here's a y value of a half here. And here's also a y value of a half right here. So this angle or this angle. But we have positive and negative, so I also have the 2 negative ones right here, because y can also be negative a half, so here and here. So again, we have 1, 2, 3, 4 times that occurs within 0 to 360. What are those angles? Well, if we see a half here, then this angle must be 30. So our angles are 30, 150, 210, and 330. These should look very familiar now. They are the same 4 angles we got when we looked at this problem the other way, the other 2 ways. Great, so it's nice to see that all these things work together. Okay, if you have a good understanding, don't feel like there's only one way to approach a problem. Let's continue with the same one and look at it even another way. So another way to solve things is to graph them, right? When we have an equation like this, we can solve it by graphing by entering one equation and entering the other one, and then seeing where they intersect. Those are the solutions. We're saying, when does this thing equal this thing? When do the 2 equations equal each other? So grab your calculator. We are going to change our window. So first of all, I'm making the window, first I pressed mode and made sure I'm in degree mode, because in this one, remember, we're looking for angles between 0 and 360 in degrees. So go to degree mode, and then you can set your window. So I'm setting my window to show from 0 to 360, because that was our domain. We want to see from 0 to 360 on the x-axis. I made the x scale 30, and that just means I want it to jump by 30 degrees. It doesn't matter what you put there, really. I made the y min -3 and y max 3. Why? Normal sine graphs go up to 1 and -1. They go as high as 1 and -1. But this one, if you remember your transformations, there's a 2 in front. It means it's being vertically stretched. So it's 2 times taller than a normal cosine graph, which means it's going to be up to 2 and down to -2. So that's why I made this y min and y max different. All right, so that's my window. Now I'm going to go to y equals and put my 2 equations in. So there's one and there's the other one. Then I'm going to press graph and check. So check yours as well. You should have something that looks like this. And then notice there's our cosine graph, there's y equals 1, they meet at 4 points. If you then go ahead and do second calc and find the intersection, you will notice the intersections will be exactly the x values we have here, the same answers we got before. It's great to see how all this is connected graphically, algebraically, using our identities. Here we go, let's try another one. This one's a little tougher. We have sine of 2x equals sine x. Okay, step 1. Notice we have sine of 2x. We can use our double angle identity for sine. So that has been replaced by that, straight from the formula we know for the identity. Now you look at this and you're like, what do I do? Well, check it out. I moved the sine over to that side so that I can have 0 over here. Because this is going to end up being like something like a quadratic problem. We're going to be factoring this to solve, all right? So now we're going to factor out a sine x. So sine x was taken out, and we're left with sine x times this. Now we have this times this equals 0. So that's just like our work in quadratics. When you have something multiplied by something and the answer is 0, then each of those pieces might be 0. Therefore, we continue by saying sine x equals 0, or the other factor, 2 cos x minus 1 equals 0. And each of those now becomes a trig equation to be solved. All right, sine x equals 0. That means when are y values 0? Well, the y values are 0 when the angles are 0. So now I'm not including the unit circle anymore. You should be familiar enough now. Think of an angle that hasn't spun at all. It's 0. Okay, the y value there is 0. Now spin the angle all the way to 180. Great, y value is 0 there again. And then 360, y value is 0 again. How about 2 cosine x minus 1? Well, take that one, solve it. It becomes cosine x 1 over 2. When you move the 1 over and divide by 2, and then you're thinking of when are the x values 1/2? Well, x values are 1/2 when you have an angle of 60 or 300. All right, that's when x values are 1/2. You can draw your unit circle to help yourself with this, and therefore all our answers are combined. All those angles lead to solutions to this equation. Great problem. Let's look at that one graphically as well. So we're going to graph it as well. We have our two equations. This one equals this one. So you're trying to see when is this sine curve equal to this sine curve. Interesting. And thinking about transformations, this 2 in front here, what does it do? All right, so I hope you're thinking, well, that 2 is a horizontal dilation, and it actually compresses it by a scale factor of 1/2, if you remember your transformations. So we're going to graph those. So keep the window as we did in the last problem. Then enter your two equations, hit graph, and here we go. You can see the normal sine wave, and you can see the one that's been compressed. So you can see the compression, and you can see all the points of intersection. There's 5 of them, and they match the 5 answers we got in the previous approach. If you do second calc, you will see the answers are the same. Great connections. All right, let's try this one. Try this one on your own, and then let's check the answer. Okay, you should have spotted this trig identity first, and then replacing it, solving, ends up being very similar to the last problem where we factor and solve. Take a look, pause if you need to. Very important that you understand this stuff. Okay, next one. Try this one out. We have this equation. We have sine 2x and cos 2x here. Before you start, your first intuition might be, oh, I see a double angle, I see a double angle. So I'm going to replace both of them with the double angle identities. Well, I'm going to let you know in this one, you are not using the double angle identities. If you made those substitutions, it would end up being something more complex. It would get very tricky very quickly. I'm going to give you a hint. Instead of using one of those, use this basic one, the very simple one. Can you figure it out? Try it out. Let's check it out. First, I'm going to divide both sides by cosine of 2x. That allows me to turn this side into tangent using this rule. So this becomes tangent of 2x. This becomes 1. Now notice again I have 2x here, but my domain is x. So I adjust the domain for 2x, making this double as well. So now I'm thinking of angles, any angle that produces a tangent value of 1. If you remember, the only way we can get tangent values of 1 is if we have 45-degree triangles, because those are the triangles where the sine value and the cosine value are the same, root 2 over root 2. When you divide those two numbers, you get 1. So the only way to get 1 is here and also here, because here we have, again, the same sine and cosine values, but they're both negative. So negative divided by negative is also 1. So our 2x values are 45-degree angle and 225-degree angle. Divide by 2 to turn it into x, and we get these two answers. Pause. That's a great question. You should take a look again. All right, next one. Try this one out. And for this one, I'll tell you the same thing. You will not use those identities. You will use our simple ones. So see if you can apply it here again. Okay, check it out. First, I square rooted both sides. Remains the same here. Then I, again, did that idea of dividing by cosine x here and here, everywhere. This turns into 1. This turns into tan. So notice we use this often to turn into tangent. Then I do like that, minus 1. Now I'm thinking, when does the x value produce negative 1? I'm thinking of an angle between 0 and 180. So between 0 and 180, the only angle that produces negative 1 is this angle here, because we have this positive, this negative, divided makes negative 1. Our angle is 135 degrees. Pause if you need to. Last one, check this out. Try it out. It's tough, but I'll leave you with this tough one. Let's see if you can get it. Figure it out. Try your best. And now check all your work. In this one, we're using this identity, making the substitution, follow the work carefully. That's a great problem. If you can understand this one, you've made great progress.